So, good morning, good afternoon, good evening, depends on where you are in the world. So, we are here today for another CASS talk. So, today we have the pleasure to have here Victor Champac from INAOE, Puebla, Mexico, that will talk about the hidden threat for manufacturing defects in advanced technologies, a potential catalyst for silent data errors. But before giving the floor to Victor, some announcements. So, next week, we have a CASS event in Panama that is a CASS Industry Forum, New Integrated Circuits and Semiconductor Technologies, Opportunities for Latin America. So this is sponsored by the CASSIF program of Circuits and Systems Society. By the way, the next CASSIF call is open till the next week, if I'm not wrong. Next week also we have the Microelectronics School and South Symposium Microelectronics in the city of Curitiba, state of Paraná in Brazil. So it starts next Tuesday. Also, I would like to invite you to participate in the next Cadathlon Brazil, that is a programming contest or programming marathon for the design automation of integrated circuits. So this will be in Maceió, in the northeast of Brazil, on July 24. Teams composed by 2 persons. So and the winners are invited to participate in the international Cadathlon that will be beginning of November. So registrations are open till 20th of June. So you still have time, but I recommend you to do the registration as soon as possible, as there is some grants for students to participate, and the order of registration will one of the items to be considered in the selection. Also, SBCCI 2025, Chip in the Jungle, the deadline has already finished, but you can still participate because the other collocated events, the deadline is still open. And this year we have a special extension that we are calling Chip in the Jungle Plus. So it will be a weekend in a hotel in the jungle with a panel about green circuits. And you have still May 12 to submit papers for SB Micro, May 14 for the Student Forum, and May 18 for Insist and workshop on circuit and system. So I hope that if you have not yet submit any papers, you still have this opportunity. This will be a very special edition. Also, Verasa SOC that turns around the world. This year is in South America, in Puerto Varas, south of Chile. And the paper submission is open till May 16, so you have still 1 week to do your submission. And there is also a PhD forum and student forum with grants for students that have a paper. You can see more details in the conference webpage. And next year, Lascas is going to Peru. That now is the location where lived for many years the new Papa. No, so you can use the opportunity also to know the region in the north of Peru where Papa Leon XIII spent many years of his life. And Arequipa, as you can see, is a very nice location. So you have still several months to prepare your papers till beginning of September. And together with Lascas, it's always organized Iberchip. So it's another option to submit the papers to these two collocated events. No? And in 2027, Lascas will be in Panama City. So where we have a new CASS chapter. No? But today we are here for the presentation of Dr. Victor Champac. So Dr. Champac was a co-founder of the IEEE Computer Society Test Technology Technical Council Latin America. He has received multiple awards and recognitions, including the Golden Care Member Award and the Meritorious Service Award from the IEEE Computer Society. Dr. Champac has delivered tutorials at international summer schools in Latin America and Europe, and has actively participated in the editorial board and the organization of international conference. He's the author of the book Timing Performance of Nanometer Digital Circuits Under Process Variations, published by Springer in April 2018. He has published over 150 papers in international conferences and journals. His research focuses on high reliability design of integrated circuits, including modeling potential failure behavior and developing algorithms and architectures for robust and dependable operation. He has expanded his work into two emerging research areas: reliable design for neuromorphic computing and robust operation of digital system under silent data corruption. So, Victor is also one of the major researchers in microelectronics in Mexico. That means in Latin America. So, thank you very much, Victor, to accept our invitation. And the flowers is with you to start your presentation.
Okay. Yes, thank you very much, Ricardo. First, I have the honor to participate in this program. Thank you very much for your invitation, and also thank you for the nice introduction. I would like to thanks also to all the audience who are participating in this talk. I am glad and honored to present part of my work. This is the title of the talk: The Hidden Threats of Manufacturing Defects in Advanced Technologies, a Potential Catalyst for Silent Data Errors. Ricardo said I work in Mexico in the National Institute for Astrophysics, Optics, and Electronics. Here is the contents of my talk. In general, he looks long, but some of them are just short. I will present some introduction to what is silent data errors, applications where there could be critical, causes, and defect challenges. I will also talk a little bit about technologies, cases, and process complexity. How is this impacting the behavior of silent data errors? Also, I am going to talk about open defects in FinFET technology. In the last years, it has been recognized by the test community that open defects, specifically resisted open defects, could be one of the main responsibles of silent data errors. There are some work on Intel about this, and other companies also. I will talk about the operating conditions. For example, IR drop, temperature, and crosstalk. What is important to recognize is that when we make the test, we compare the condition during the test and the condition during real operations, they could be different. So this is going to impact that we do not detect some defects or some faults for some chips. We are analyzing the impact on circuit behavior under wideband constraints. Finally, I will give you some conclusions. This is the main definition of what is silent data corruption. Silent data corruption is also known as silent data errors. A silent data error is an altered or corrupted data in a computer system that goes undetected by hardware or software checks of the systems. The system, as you know, the computer system has many mechanisms to protect, but the corrupted data in this case is not detected. Here, example, some checking mechanisms. You have error detection codes, logic level checks, redundancy, etc. But there is no alert for this. The term silent refers to the lack of alerts, letting corrupted data affect system behavior unnoticed. This is the key point of data corruption, that they are happening, but the system does not know that they are there. EDCs are an increasing challenge for data processor centers. For example, Google, Meta, they have reported critical events related with silent data errors. One of the main problems of silent data errors is that they are very difficult to debug, to diagnosis. So this could take months even for knowing the root cause of the problems. As you don't know, Google, Meta, data centers, they use millions of chips, because this grand amount of chips, they are quite susceptible to SDS. Another potential application where SDA is critical is automotive. This is quite interesting because automotive use a less number of chips than data centers. Some chips in automotive right now are made in advanced technology nodes. But why is critical in automotive? Because a single silent data corruption can put life on risk. So this is critical. Okay. So another point is another application where this is critical is financial systems, for example. Okay. Also aerospace, aircraft, for example, medical application where the life could be under risk. Why are we worried right now about silent data corruption? Actually, silent data corruption already existed for many decades. But why now? Why now we are a bigger concern about this? One of the reasons is that scaling technology. Right now we have advanced nodes like 5 nanometers technology, like 3 nanometers technology, scaling technology, and rising system complexity have turned SDC into a critical reliability concern. This is the difference of SDS from the past and the complexity that we have known. For example, we have the Adam Crow, this is a researcher from Synopsys. He has commented that it is possible we are facing defects coupling with design marginalities. This is and this is leading to SDS. What we have is chips passing production tests, then fail in the customer environment because the operating conditions again during real life is different than during tests. So this just a little push to any marginality puts the chips over the edge between good and faulty behavior. Among many seeds, we need to know the root cause. Some failed behaviors right now are not understood by industry and academic communities. As you know, the technologies are evolving very fast, and the technologies are coming with more complexity during the process, during manufacturing. For example, here we have with scalings the trends. Here you have an example from 32 nanometers planar CMOS to 14 nanometers FinFETs. Right now we have technologies in 5 nanometers and we are going to 3 nanometers. So what we have is increased susceptibility to silent data errors as the technology scales. Here you have a planar CMOS device, and here you have the image of a FinFET transistor. In this case, we have 3 fins. Why? So why we have more susceptibility to silent data errors at smaller nodes? First of all, we can say that smaller transistor sizes, 5 nanometers, 3 nanometers, we have reduced charge per node. This means that we need less energy to flick the devices. This increases vulnerability to cosmic rays and radiation. We also have lower supply voltage. This means less noise margin. We also have, at the smaller nodes, higher density and coupling. Denser integration means closer proximity of wires and gate. Means increased parasitic coupling capacitance. This means more crosstalk. Okay. Also, at the smaller node, we have process variation at a smaller node. This is a quite important problem. We know from planar CMOS, the problem of random dopant fluctuation was reduced passing from CMOS to FinFETs. However, right now in FinFET, we have a strong variability of at the gate because the word function. Also, we have new design practices. I will make a special emphasis in the new design practices. Actually, some of these design practices were used partially in subchips in CMOS planar. But right now, because the structure of FinFETs, they are using intensive. Here you have the FinFET transistor. This is, as you know, this is a three-dimensional device. We can have current at the 3 volts of the device, this size, the other size, and also in the upper size. What we also have in FinFET technology? FinFET technology is using a strong middle of line interconnection. This means for making connection in the internal gates, we use special layers which are responsible of this function. More importantly, how do we increase the driving capability in FinFET technology? Normally, for planar CMOS, when we want to have more driving capability, more current, what we do is to enlarge the active area in the direction of the gate, of course. So in this way, we have more current and we can manage larger capacitance. For FinFET, this is not possible. What we actually have is fins, for example. This is a fin, and in this case, we have 6 fins. And here we have the gate. So when we crossing between the gate and the fins, we have channel current. So if we want to increase the current, we add another fin. We are not able to change the sizes, the dimensions of the fins. They are fixed. Okay. This means that the driving capability is discretized. This is, we want from this one unit to second unit, but we cannot have anything in the middle. Yeah, and so this is called a multi-fin device. But we also have a multi-finger device, as in this case to the right. In this case, horizontal, we have 3 fins, but we have 2 gates here, gate 1 and gate 2. For FinFETs, the gates are known as fingers. So we have, as you can see, the driving capability of this multi-fin device is similar to the driving capability of this multi-finger device. Okay, we can use them as we desire in our layout. This is important because we have more control of the height of the cell. However, we cannot say that the dynamic behavior of both devices is exactly the same. There are some differences because the coupling parasitic capacitance. Okay, in the geodesize praxis, here we have the layout here of a multi-finger inverter. And here to the left, you have the schematic of this inverter. This is an inverter. Actually, this schematic mimics how the layout has been routed. Okay, so how is this made? Here we have 3 parallel things here for having certain driving capability. And in the PMOS network, we have another 3 transistors. PMOS transistor and EMOS transistors, they share one common gate. This is called finger. And if we want to have more driving capability, we can put a similar structure in parallel. We put the gates together and we put the output together. So in this case, we have. This is very interesting because this way of designing is going to impact the test. How do we make tests? This is as you already know. This is my circuit under test. This is the chip that is actually fabricated. Normally, we apply test vectors. We make an output observation. For a given test vector at the input, we already know the expected output response. And this is called reference. We make a comparison between our expected response and the measurement. If they agree, we say that the circuit passed. If they do not agree, the circuit failed. It's considered a bad circuit. Okay? The test vectors are going to depend in the type of test that we apply. We have Boolean tests, like Stukat, for example. Well, okay, we also have more complex tests, like transition fault tests. This is a different type of vectors. We also have small delay faults, cell-aware tests, and so on, different kinds of tests. Okay, Stukat, the more basic tests like Stukat 0, Stukat 1, they are not capable to detect more subtle defects. In order to detect more subtle defects, we need more complex tests. Okay, here we have, let's say, a group of chips, a group of chips. So, what we are a group chip with defects. Here we have in this area known defects. Yeah, here we have unknown defects. Normally, we make to the chips our test. Some of them they fail the test. Of course, most of them are good, and some of them are bad. It's interesting in the right side, these chips pass the test. This means that the test does not detect any problem with these chips. So the point is if some bad circuits, especially those having critical paths close to the edge clock, may become silent data errors. Okay. Let's talk just a little bit about open defects. Here, the classical way that we have open defects is because we have an opaque particle, and this is sensitive to the lithography process. Here we have a broken line. Also, for FinFET technology, we use spacers, for example, in FinFET technology. If we can have line cuts, in this case, this is in the spacer, and this one in the material, del polymer material. And this leads to open defects. Open defects could be fully open, completely disconnected the lines, or partially disconnected. This means there is a resisted open. We also can have via voice. This is when the vias, the contacts, are not filled correctly through the walls. Okay, here we have, I am going to talk here about full open gate location. This is when the open completely disconnect the line. We can have here different locations. This is the red cross here, different locations. This is quite interesting. This is a multi-thing inverter. In this case, this is one finger, second finger. This is the third finger. So yeah, this is quite interesting. Let's say that we have this one is failing, and we have to discharge the output. First of all, we can see that these two things are working correctly, and the other ones are working correctly. What means that having this open here, this inverter is going to work correctly from the volume point of view. This is a quite different behavior to CMOS planner. We will have always a range of open defects failing during volume. In this case, the open never fails a volume test. So, if we see about delayed, okay, one of them fails, but we have 1, 2, 3, 4. We have 3, 6, 8 things working correctly, and one is failing. If we want to discharge the output through these things, the delay will be small. So let's see some plots. Here we can see this is the static behavior. This corresponds to a volume test. And we can see here the input is high, a high value. And we see that the output is always a low value. In this axis, we have the voltage on the float on this node, on the floating point. This is a particular characteristic of this defect. In this other case, for the other input, this is another vector. When we apply a zero logic, the output is always one logic. So this open is not detected by any volume-based test. What about delay? Let's take a look to the dynamic behavior. What we observe that there is a range of defect, a range where the delays are small. In this axis, we have the delay, the normalized delay increase, and here is a parameter characterizing the open. What we see is in this range, delays are small, but the delays increase in this area. For the other vector, the delays are very, very small. Okay. Let's go now to resisted opens. This is critical, as we will observe. In this layout, we have different type of resisted opens. We can have resisted opens at the drain source of the transistors. We can have a resisted open affecting a single transistor. And we can have also IR up, interconnect resistive open. This is a resistive open that affects at the same time one NMOS transistor and one PMOS transistor. So here you have bit crosses, different open locations. Here is the behavior for these opens. What we observe that for the three types of defects, for this one and this one, resisted opens at the drain and resisted single transistor, we have that the delay increase at most 30%. Okay, this is quite different to the full open case, where in full open case we can have even 100% or more of the increase of the delay. So this mean and resisted opens, this case and this case, these opens will be more difficult to be detected. For this open here, we can have a higher delay increase. It is likely it is more likely that they will be detected by a delay-based test. But however, I want to make emphasis in these two types of resistive opens that will be difficult to be detected. So let's take a look to the operating conditions affecting a marginal chip. As I said, first, what is a marginal chip? A marginal chip passes the test, but operates near failure. This means near the clock edge, making them sensitive to real-world conditions. Normally, the real-world condition or working conditions are not exactly the same than during tests. So, what are the operating conditions that could affect to these marginal chips? The conditions can be static and dynamic IR drop, for example. Crosstalk, temperature variations, process variation. We have chips with different process variation, aging effects, electromigration. And we also, this is less, less understood sometimes for the test community, we also can be affected by humidity, mechanical stress. Actually, chips for automotive application, they are tested strongly if, under conditions of humidity and mechanical stress. Okay, and the question is, what delays could be silent data errors? We have called them as potential silent data errors. Those delays that could be that during the test, the chip passed the test, but they could be silent data error. So here we have this axis, critical path delays of chips. And here we have the clock edge. In this ray, we have some warp band. So this is the clock edge. So the lights here close to the clock edge could be potential silicon data errors. So some of them, during real life conditions, could fail. And as a consequence, these are potential silent data errors. So these are our big concern. This is what we called before a marginal chip. Let's talk briefly about IR drop. I guess most of you already know IR drop. So we know the IR drop is the supply voltage loss from interconnect resistance and circuit current. No? Here we have a map of IR drop. Basically, the voltage at different point of the die changes the power supply voltage. And we have that as a consequence, reduced VDD, increased path delays, we know that. Delay spikes beyond their allowed timing windows may cause setup and hold time violation. Also, we know that timing failures due to IR drop may not trigger functional fouls, resulting in undetected data corruption. Another interesting point is that advanced nodes operate with lower power supplies and tighter timing margin. Because of this, they are more vulnerable. Temperature. This is another important, how the temperature changes during the working operation of the chip is quite important for their behavior and for the detection of possible defects, especially those chips having defects working at the edge of the clock. For example, here we have how it is the power density in a die. This is the reference. And here we have that the temperature is different in the die. No? Of course, at the center here, we have more activity, and here we have a hot spot. Okay. When we move away, we have colder areas. So we know that higher switching frequency leads to more heat. Work log is very important in this case, and the hot spots. So this IR drop and temperature, they are not exactly the same during test and work and real work applications. Crosstalk. I will show just a simple example how crosstalk is quite interesting for tests. Here we have this circuit, for example. This circuit has a full open defects. As we can see, we have this is a line we say that this line is floating. Okay, it's totally disconnected here, and this line suffers different couplings, 1, 2, 3 couplings. Okay, the final behavior at the output of the inverter is defined by the voltage at this line. What we observe is here we have different here, and here. You have different inputs, different activity at the coupling lines. What we see here is that depending on the activity, the voltage at the input of this inverter change. And as a consequence of these inputs, we observe also that the output change. We can have the behavior going to 0 or the behavior going to VDD. So this means that if we don't take into account the crosstalk, the crosstalk signals during tests, this defect could not be detected. So this is the importance of having crosstalk. But anyway, generating test vectors considering crosstalks is a more expensive test. So in many cases, this is not considered, or maybe this is taken for just a small success of paths. But let's see about real example of real life operating conditions on delayed. We are using this logic path. This is a logic path. Here we have the normalized delay increment. And this will be our, we are going to inject these operating conditions at the defective gate, only at the defective gate. For example, a IR drop, 10%. Crosstalk, we are going to consider 2 capacitance. Temperature, to range minus 50 degrees and 100. Here is the behavior for IR drop. This is the nominal behavior, and here is with IR drop. This is the delay, the normalized delay increase of the logic path. So from here we can see this that there is here is around 30, almost 40% of delay increase, and in this case we have more than 60% of delay increase. Okay, this is this curves. This is when one thing is affected by the resisting open. In this case, 2 things affected by the resisting open, 3 things affected by the resisting. As more things are affected for the resisting opens, we have more delay increase, and we have more possibilities to detect the defect. But for when you have 1 thing or 2 things, we can see that even here the delay is very small. It's very difficult to be detected by a normal test. So crosstalk. Here we have crosstalk for the 2 capacitance. If we compare this curve with the previous, we can see that the delay also increase. The increase for these 2 capacitance values that we have considered, the increase is lower than for IR drop. And temperature. Temperature, this is also important. We can see that also the delay increase depending on the temperature. For FinFETs, we have to take into account that the temperature behaves different to the CMOS planar. Okay, for FinFETs, we have a phenomenon called inverse temperature effect. Okay, this means that as the temperature increase for FinFETs, the delay decrease. This is known as inverse temperature effect. Okay, let's take a look to how these affect the relation with silent data errors, failures, under ground bounds. Okay, here we have a logic path. This is a critical path. This has been taken from CASS benchmark circuit. And we are going to inject defects at this gate, this yellow gate. So again, the same condition, we are going to consider the same conditions. 10% IR drop. Just one single capacitance in this experiment, 0.5 at this temperature. And most importantly, we are going to consider two ward bands constraints. One of them is 10%, and the second is 15% of the path delay, two ward bands. So in this case, we have a more realistic example how the resisted opens and how the defects could turn into a silent data error. Here we have, this is the delay of the logic path. And in this axis, we have the value of the resisted opens. In this upper plot, we have the resisted open affects one thing, and in this case, the resisted opens affects four things. What we observe is that when the ward band is 10%, this is here, this is the nominal characteristic. This is the nominal behavior. This means the nominal behavior means when we do the nominal VDD without coupling capacitance and nominal temperature. Okay, so in this case we have when we have coupling capacitance and we see the delay increase, but in this case this chip is accepted as good because we are below the ward bands. When we add another effect, in this case was VDD, and in this case is VDD mass crosstalk. Sorry. Okay, when you have VDD mass crosstalk, again we can observe that the logic path is not able to pass the ward bands, so the chips are considered as good. Okay. Again, the last case here is when we have IR drop, crosstalk, mass temperature. So in this case, we can see that just some chips may fail for this ward band. Of course, if we have a larger ward band, this means that tolerate more delay. So none of them is detected by a delay-based test. This is when the resistive open affects only one thing. Affecting one thing implies lower delays. Now we will see how is the behavior when more things are affected, as in this case, in the lower plot. In this case, you can see that the delays are larger than previously. So in this case, we can see for the we can see that this is the 10% ward band, and this is the 15% ward band. So we can see that in this case, only having IR drop, we cross the ward band. So these defects will be considered, this chip will be considered as defective. We can also observe that if the ward band is larger, these chips are not bad, are considered as good. Okay, so here we can see that when, important to say is, when more things are affected, we have larger delays. We can have the possibility that that fails. When we have smaller delays, some of them can be considered as good chips. But if these good chips are marginal, this could be a problem for silent data errors. Here is a quite interesting plot. In this axis, you have the affected things, and in this axis, you have those resisted opens that could be potential silent data errors. This case is for a warband 10%. And in this case, we have a warband 15%. What we observe it is interesting to observe the following here. When one thing is affected, we have small delays. Okay, so we need to increase the resisted open for having more delays. Even so, the delays, when one thing is affected, the delays are close to the edge. So they are considered as good. Only this region could fail for one thing. Only from here to here, for one wing affected, this could be considered as potential resisted open. I had to remember that if the chip is already detected during test, the thing is already considered bad, this is not a silent data error. A silent data error is the chip having a defect but working close to the edge clock. So when we have two things, we have more delays. The delay increase, okay? The delay increase. So if the delay increase, even smaller resisted opens could be silent data errors. Okay, and this behavior continue for 3, 4, until 5 things. Okay. For 6 things, this is quite interesting because for 6 things we have more delays. These delays here are high enough, so they already fail during the test. See, if they already fail during the test, they cannot be silent data error. However, these ones, they are silent data error. Okay, this is for 10%, and this is for 15% of warband. This is quite interesting. As you see, when we have a 50% of warband, this means a larger warband. Okay, as you can observe, we have less number of potential resisted opens that could be silent data errors. Okay. Why is this behavior? Because the delays, when we have a larger warband, we have a more tolerance to defective delays. So what we have is, I would like to comment at this slide is that we have a lower number of potential silent data errors as the warband increase, as the tolerance, as this tolerance increase. But we have to consider that if we have a larger warband, we also lower the speed of the chips. So this is not a complete solution. We need to make more research on that, having some trade-off, but customers, they will not be happy having slower chips. So finally, I want to go to the conclusions of my talk. I could mention that environmental and workload-induced condition, a drop as I see, temperature, crosstalk, can silently degrade performance, turning marginal paths, marginal chips, into undetected failures. Resisted open defects in advanced FinFET technologies can trigger silent data errors. Reduced warband in scale technology increase vulnerability to silent data errors. But we also have the opposite case, as I mentioned before. We know that with the complexity of scale technologies, current tests may miss subtle delay defects, stressing the need for better fault models and timing-aware strategies. To ensure reliability in critical systems, designs and tech practices must consider real-life conditions and hidden defects. With this, I conclude my talk. Thank you very much for your attention. I guess we have now some time for question. Ricardo commented.
Okay, thank you very much, Victor, for this very nice, interesting talk. So we have here one question by Ulisses Mafazioli from the graduate program Microelectronics of the Federal University of Rio Grande do Sul. So with more errors from short channel effects, when should we tolerate faults and when should we invest in better detection?
Okay. This is a quite interesting question. I will say that the two approaches, having better detection and increasing fault tolerance, some, let's say, different opposite ways of addressing the problem. Okay, as we have more fault tolerance, it will be more difficult to detect the problem. But the system is more robust, of course, no? Okay, so, this is a point. But with short channel effects, but for being more specific to your question, short channel effects, when you told me about short channel effects, I think about process variation. So we can add some design strategies to make the chips more tolerant to process variation. Okay, is that okay? The question, is that okay? The answer for you?
Thank you. So I see no more questions here in the chat channel. So if someone has another question, please do it now. So I can have one for Victor. So there is always a compromise between doing circuits that are more reliable itself versus circuits that we are going to do verification if there is an error, and then to use some voting, for example. And so how can you talk a little bit about this issue?
Yeah, that is these approaches are quite interesting. We actually don't know. We have different strategies for making a circuit fault tolerance. No, we can, from the board single one having duplication, triplications, but there are also more sophisticated ways. And also, we can add some error correction techniques also in hardware. Okay, but the defects are more difficult, I guess. Having more tolerance, let's say, makes the test more difficult. So maybe, and this is just my pause. We can add a way to change to add some switches into the circuits. Then we have less tolerant, some tolerant circuits. We separate the tolerant circuits, so they lost. Let's say they lost some tolerance during test. Just for test. When, in this way, maybe we can make more robust the chips. Okay, this is just my thoughts.
Okay, thank you. We have here a question by Poncho Cabrera. So Poncho Cabrera is a PhD student at Duisburg-Essen University. So the Poncho says, thanks a lot, Professor Champac, for your interesting presentation. My question is, could the tolerance of the digital cells to manufacturing process conditions errors be improved by a more robust design.
Okay, this is an interesting
He
question.
also adds at individual cell level.
Okay. Okay. Okay, this is the approach of the fault tolerance. Usually, how we approach increasing fault tolerance for cells or for a circuit, no? As far as I know, one of the main strategies is making that robust to any 1-0 fault behavior. This means we use many times a stuck at 0, a stuck at fault model, but even there are some work in other fault models. Okay, when we translate this to manufacturing process conditions, at tolerance, this means adding tolerance at a lower level. This means adding some tolerance at transistor levels, and even in the cell, having different configurations, we can have also more tolerance. Actually, there are in the literature, and actually the industry use, for example, flip-flops, logic cells, tolerance to process radiation, for example. There are different types of cells where they add transistors for this. I guess some of these strategies we need to analyze could be considered when we consider variations in the process, the effects during the process. When we talk about the manufacturing process, this is a lower level of abstraction of the problems. So we need to translate properly the strategies.
Thank you very much. So I see no more questions. So just I would like to thank you again, Victor, for the nice talk. And it was a great pleasure to have your talk today here. And so I hope to see you in person soon. I also would like, before closing this session, to remind you that you can still submit papers for the Chip in the Jungle. So SB Micro Student Forum insist and WCASS, the call for papers are still open. Besides the SBCCI 1 is closed. So in SBCCI, we have 50% more papers submitted than last year. So this is a good news. And I also recommend you to consider to do the extension of the event in the hotel in the jungle. So this is a unique experience, and we are going to have also a panel in the hotel in the jungle about green circuits. No? So I hope to see you all there next end of August. And also, you can still have the possibility to submit for the Verasa SOC that this year in South America, and the submissions are open till May 16. And you have also the PhD forum and the student forum. And if you go to the web page, you will be able to see that there is 3 possible grants to help with the travel of students with papers in the event. No, grant from IFIP for PhDs and the students from the emerging countries, grant from IEEE Calcium EDA, and grant from IEEE Circuits and Systems Society. So don't lose this opportunity to go to this international conference that this time is being organized in South America. So the next years will be in locations in other continents. So thank you very much. Soon we are going to announce the next CASS Talks, and you can always take a look in this YouTube CASS Rio Grande do Sul channel to see the announcement of next ones. So thank you very much to all you, and we are going to close this session and wishing you a nice weekend.
Thank you.
Bye-bye.